where is indoor positioning going? Is what the elements that we have, how are they evolving? All these elements. Dr. Paul Groves is an associate professor at UCL, where he leads a program of research into robust positioning and navigation. He's interested in all aspects of navigation and positioning, including multi-sensor integrated navigation, improving GNSS performance under challenging reception conditions, and novel positioning techniques. He's author of the book Principles of GNSS, Inertial and Multi-Sensor Integrated Navigation Systems. He is the recipient of the 2016 Institute of Navigation Thurlow Award and a Fellow of the Royal Institute of Navigation. He holds a bachelor's degree and doctorate in physics from the University of Oxford. So, Dr. Groves, the stage is yours.
Hi, everyone. Can you hear me okay?
Yes, perfectly.
Okay, right. Let's get the presentation up and running. Right. Okay. Select the PowerPoint. Okay. Presentation mode. Okay, Chair, can you see the screen okay?
Yes, we can see it.
Okay, great. Okay, let's start. Okay, so thank you to the IPN 2022 committee for inviting me to give this presentation. So to give you a bit of background, I'm not an indoor positioning specialist. I'm interested in all sorts of navigation technologies, both indoor and outdoor. So I'm going to be taking a look at where I think indoor positioning might be going over the next few years. So first of all, we'll look at the state of the art, look at all the different indoor navigation and positioning technologies, and explain why Wi-Fi dominates consumer positioning so much. Then we'll be looking at the evolution of Wi-Fi positioning from signal strength to round-trip timing, how this can improve the accuracy, and the many challenges still to address. Then I'll be looking at how we might augment Wi-Fi positioning with other technologies in smartphones. Is integrated navigation the right approach for smartphones, and which technologies should be used? And then finally, I'll be looking at, is it time to unite indoor and outdoor positioning? Are they really separate fields, or should we consider it as one problem? So the first topic is looking at the state of the art. So we can divide indoor positioning and navigation technologies into 4 categories: dead reckoning, optical positioning, signals of opportunity, and finally beacons. So I'll talk a little bit about each category. So with dead reckoning techniques, we start at a known position. We measure the change in the position or the velocity. We then sum the position changes or integrate the velocity in order to give us our current position. And there are many different technologies that we can deploy. For a pedestrian, indoors or outdoors, we can deploy pedestrian dead reckoning using inertial sensors to detect steps and estimate the distance taken. If we mount an inertial measurement unit on a shoe, we can then perform inertial navigation and perform zero velocity updates every step to limit the solution drift and keep the system calibrated. For robots and vehicles, we have wheel speed odometry, and then for applications where it's convenient to have a forward pointing camera, we can also deploy visual odometry. So these dead reckoning techniques, they have advantages and disadvantages. So the main advantage is they'll operate continuously by hardware faults, and they don't require any external infrastructure, signals, or landmarks. But the big problem is the position error increases with time in proportion to distance traveled. Because you're adding measurements together all the time to compute your position solution, you're also adding errors together all the time. So as time increases, your error gets bigger and bigger. And determining the direction of travel can also be difficult. So dead reckoning is a useful component of an integrated system, but it's not very practical on its own. So the next class of systems is optical techniques. So first thing I'll be talking about is motion capture. So the person or object that you're tracking is implemented with lots of markers, multiple high-speed cameras in the room, then capture images from different angles. And this gives very, very high accuracy. You can achieve sub-millimeter performance, but the problems are it's expensive, wearing markers is inconvenient, and it's really only practical to deploy for individual rooms. So it's not going to work for an entire building or an entire city. Applications include film and video game production, biomechanics and medicine, and then augmented and virtual reality. A simpler approach that can use a basic smartphone camera is landmark recognition. And there are different ways that you can do it. The way humans work is we recognize features such as a window, a cabinet, a desk, carpet, and so on. We now have algorithms for identifying features from camera images. The technology is still developing, but it's getting better all the time. So we can now identify features in an image, compare that image with a database, and use that to determine our position. The older approach to landmark recognition is whole image matching. So you take the captured image, you typically identify corner features in that image. They're compared with an image database where corner features have also been extracted. The best matching image is selected, and wherever the camera position was to take that image in the database, that's the position solution. So considering the way humans think, it's a less natural approach, but the technology is more established. But I think the feature recognition approach is the future. For all of these landmark recognition techniques, the accuracy and reliability can vary a lot. Things that affect it include the equipment quality, the quality and size of the database used, and the sophistication of the algorithms. And a big problem with landmark recognition is repeating features. So here we have a hotel corridor, and you can see that the same features are repeated again and again down the corridor. So it's very difficult to work out which part of the corridor that you're in. So in terms of practicality of camera-based approach, forward-pointing cameras are fine for a robot. Most of them have cameras, but it's inconvenient for a smartphone. So if you're currently using the smartphone, it's typically going to be held at an angle rather than forward-pointing. And then if it's in a camera, if it's in a pocket or a bag, then the camera is not going to be accessible. These systems are also typically more computationally intensive than radio-based systems, and building the database of landmarks adds to the cost, although simultaneous localization and mapping can automate this process. Okay, the next category of indoor positioning technology is signals of opportunity. So this is using existing radio signals that are designed for other purposes. So a big advantage is you don't need to spend money on infrastructure because that's already there, but you've still got to create a database and you have to deal with signals that are not optimized for positioning purposes. So radio and TV broadcasts, mobile phone signals have been demonstrated as possible signals of opportunity. So these have the advantage that they're widely available indoors, but receiving the signal isn't sufficient. How to obtain a position solution is more difficult. So simple proximity positioning, as in I can receive this signal therefore I must be here, isn't really viable for these signals. Radio and TV broadcasts cover an entire city, and even mobile phone signals cover quite a wide area. So that's not going to be very accurate. For ranging, you need to be having signals coming in from several different directions, and you may not always have that. I mean, you may only be picking up TV broadcasts from a single site, for example, and how many phone masts you can receive signals from varies on where you are. Another big problem with these technologies is that non-line of sight reception is a big problem, unless the transmitter is very close, because with these terrestrial signals, they're all low elevation. So there's no guarantee that the signals are being received directly. So great for developing research papers, but not necessarily very practical. Now, Wi-Fi positioning is also a signal of opportunity. So Wi-Fi was deployed for internet connectivity, not for positioning. It's widely available. You can receive Wi-Fi almost everywhere indoors. All smartphones have Wi-Fi radios, and the short range of the signals minimizes positioning errors. So the strongest access point is usually within 30 meters, and Wi-Fi signals don't travel more than 100 meters. So provided your database is correct, Wi-Fi positioning errors are never going to be more than 100 meters. Multiple access points are usually receivable. So by positioning using received signal strength measurements from multiple access points, an accuracy within 10 meters is usually available. Google and Apple provide free use of their Wi-Fi positioning algorithms and databases on their phone systems. And because of all these advantages, Wi-Fi is by far the dominant indoor positioning technology for smartphones. Final category of positioning techniques I want to talk about is beacon systems. So early indoor positioning systems were based on infrared, ultrasonics, and active radio frequency identification. None of these technologies made it into smartphones, so they're essentially consigned to history. More recently, we've had more interoperable beacon technologies. So Bluetooth Low Energy is compatible with smartphones, and then the indoor messaging system, IMES, can be used with a modified GNSS receiver, which is also included in a smartphone. But the problem with these beacons is all of these systems require beacons to be purchased, deployed, surveyed, and maintained, i.e. changing the battery so that they keep working. And the accuracy that they provide is no better than Wi-Fi positioning. So there's no reason to spend money and effort deploying the beacons if you're going to get the same accuracy as you're already getting from the existing Wi-Fi. Ultra-wideband positioning, however, is different. So ultra-wideband is defined as a transmission which has a bandwidth which is either greater than 500 megahertz and/or a ratio of bandwidth to carrier frequency which is greater than 0.2. So this is a diagram of the power spectral density versus the frequency. And here we have an ultra wideband signal and a narrowband signal. So because of the wide bandwidth, UWB has to share spectrum with other users, typically 3 to 10 gigahertz. And to avoid interfering with those other users, the power spectral density has to be very low. And then spread spectrum techniques, like are used for GNSS, are then used to recover the signal information. So for range measurement, multipath has one very big advantage. The very high bandwidth enables excellent multipath resolution. So in a typical indoor environment, we might receive a direct signal and several reflected signals, and the direct signal may be weaker than the reflected signals. if, for example, the direct signal has passed through a wall, whereas reflected signals pass through a doorway. So with most positioning technologies, these signals would all merge together and be difficult to distinguish. But because of the high bandwidth of ultra-wideband, they can be easily separated. So you can just assume that the signal received first is the direct component, and that's the one you want to use for positioning. So ultra-wideband gives you meter accuracy in difficult environments. Under ideal conditions, where all signals are direct line of sight, you can get centimeter accuracy. Without obstruction, the signals can carry for hundreds of meters. And if there are obstructions, signals can pass through one or two walls and still be usable for positioning. Many different architectures are used, remote positioning and self-positioning, and different ranging methods. So historically, ultra-wideband has been relatively expensive, and as a beacon system, you've got to pay for the infrastructure to deployed. So it's become established primarily for professional indoor positioning applications where it's the technology of choice. So this includes tracking equipment, components, products, and people in factories, warehouses, and hospitals, and also tracking firefighters and other emergency personnel inside buildings where the Wi-Fi may not be working, and if you have limited visibility due to smoke, you want a much higher positioning accuracy anyway. So you can set up ultra-wideband beacons just outside the building, determining their position using GNSS, and then as the emergency team passes further into the building, they can drop ultra-wideband relay beacons to extend the service further into the building. And there's lots and lots of different companies that provide ultra-wideband products and services. I've put 8 company names on the slide, and there are many more. So in summary, the dominant techniques for indoor positioning are ultra-wideband for professionals because it gives the highest accuracy and is much more practical than optical systems. And then Wi-Fi for consumers because the infrastructure is already there and it's practical to implement. So for the rest of the presentation, I'll be focusing on the smartphone-based consumer applications. So our next topic is transitioning Wi-Fi positioning to round-trip timing. So currently, smartphone Wi-Fi positioning generally uses received signal strength based ranging. So a model is used to estimate the distance to each access point from the measurement. Then the position is then calculated from the distance estimates and an access point position database, and the accuracy is typically 5 to 10 meters. And the reason it's not better is that the received signal strength can vary a lot for a given range. So here we have a graph of received signal strength versus range. So the model shown in red assumes that the signal strength drops smoothly as the range increases. The blue line shows what happened in reality. You get lots of variation and you can get the same received signal strength at different ranges. And there's lots of different reasons for that. The signal may be attenuated by the phone user's body. There may be directional variations in the antenna gain at both the access point and the mobile. Multipath interference due to reflections from the ground, walls, and other vertical surfaces can affect the signal strength, and reception may be non-line of sight, which drops the signal strength. So for accurate positioning, we need a new approach. So within the research literature, lots and lots of different institutes have demonstrated received signal strength versus positioning. So here you measure the signal strength from all the receivable access points, compare it with a database of measurements made on a grid of different positions and select the best match, or more commonly, several best matches. And this gives you your position solution, typically within a few meters. So better than the standard smartphone approach. But there are big problems. First of all, building the database is time consuming, adding cost. Google and Apple don't have access to every building, and the building owners don't necessarily want to spend money building a database. And then moving furniture, opening doors, and people moving all change the received signal strength. So let's think about a completely new approach, Wi-Fi round trip timing. So either the mobile or the access point sends out a signal to the other device. After an agreed time, the other device responds and sends a signal back. So the total time we call the round trip time. If you then subtract the response time, divide by 2 and multiply by the speed of light, you've got a measurement of the range. But we have the problem that actually the intended outgoing signal transmission time is different from the true, and the measured final incoming signal arrival time is also different from the true time. But both of these timing offsets happen at the same device, and because we're subtracting this time from this time, the 2 time offsets more or less cancel out, and the response time at the other device is assumed to be known. So by performing 2-way ranging, we cancel out most of the clock errors. We do get a residual timing effect due to base and mobile frequency offsets, but the errors are much smaller. So in 2016, a round-trip timing protocol known as fine time measurement was added to the Wi-Fi standard as part of the 802.11mc version. And this is intended to offer a sub-meter range measurement precision. So what are the error sources that affect round-trip timing? First of all, we have measurement noise. So noise affects any type of measurement. The FTM protocol comprises bursts of 8 round-trip timing measurements. So these provide enough information for an SD of the measurement noise to be computed, and the noise is usually sub-meter. So measurement noise is not a big problem. We then have mobile and access point hardware biases due to oscillator frequency error. So these are supposed to be less than a meter, but we're reliant on the manufacturers conforming to this requirement. We then have multipath interference due to reflections from the ground, walls, and other vertical surfaces that interfere directly with the received signals, but the short path delays we get because Wi-Fi doesn't travel very far, combined with the high bandwidth, limit the ranging errors. So usually multipath errors are less than a meter. So far, so good. However, our fourth error is non-line of sight reception. So this occurs when the direct signal path between the mobile and access point is blocked, and we're receiving the signal via a reflected path, or the reflected path is just stronger than a direct path. In this case, the ranging error is the difference between our longer reflected path and the direct path that we're trying to measure, and this is usually more than a meter. So non-line of sight reception prevents us reaching our accuracy target for Wi-Fi round-trip timing, so we need to do something about it. So the GNSS community has been looking at means of mitigating non-line of sight reception for several decades now, so we can look at some of the techniques deployed by the GNSS community and see if they're applicable to Wi-Fi. So first of all, we have 3D building models. So these predict which signals are blocked, and with a bit more computational load, they can correct non-line of sight path delays. The problem is indoor 3D models are much less available than outdoor 3D models, and we need to consider furniture as well as walls. So 3D building models is not really practical for wide deployment at the moment. The next technique used in the GNSS community is consistency checking. So we assume that direct line of sight measurements will provide a more consistent solution than non-line of sight measurements. So we can use the residuals of our solution to find the most consistent set of measurements to use to compute our position solution. But this technique works best when there are more good measurements than bad, which we can't necessarily guarantee in an indoor positioning scenario. So then the final approach is signal strength. So non-line of sight measurements tend to be weaker than direct line of sight measurements. So we can use our round trip timing measurement to predict what the received signal strength should be, compare it with the actual received signal strength, and if there's a big difference, then that's a potential outlier, and maybe we should reject that measurement. So we have here a few results generated by my PhD student, Gibran Raja. So in this diagram, the red point here is the mobile device. The green points are access points. So most of them are direct line of sight, but we have a non-line of sight access point here and a non-line of sight access point here. So in blue, these dots here show us the position that we get if we compute a simple least squares solution using all of the access points. In black, we have the position solutions obtained if we use signal strength based outlier detection. So you can see these are much closer to the true mobile position, and in the best case, this outlier detection technique is reducing our position error from about 2 meters to about 20 centimeters, noting that the AEB mobile biases due to frequency errors have been calibrated for this. Gibran also tried residual-based outlier detection, but in this case, it didn't work. It just gave the same results as the all access point solution. So we think that signal strength-based outlier detection is the way forward to limit non-line of sight reception errors. Now, round-trip timing only works where both the access point and the mobile device are compatible with that technology. So several compatible phones are available from Google, LG, Samsung, Xiaomi, and many others, but access points is a problem. So pre-2016 access points will obviously not support the fine time measurement standard. And currently only Google offer fully compatible access points. There are some partially compatible access points available. They don't advertise the RTT capability in their beacon frames, but they will respond to requests for a FTM round-trip timing ranging message. However, the hardware biases may be outside the specification, so these access points may not give the meter accuracy that's required, and these are all for home use. Companies targeting business users of Wi-Fi are only just starting to offer products that support the FTM RTT standard. So why might that be? Well, the issue is that this standard was a midlife upgrade to the 5th generation of Wi-Fi. So many manufacturers are waiting for the full Wi-Fi 6 to come along before they upgrade the equipment. So the new Wi-Fi 6 standard was finalized early last year, and this actually incorporates a new round-trip timing protocol called next generation positioning. So hopefully with Wi-Fi 6, we will start to see more deployment of round-trip timing. Android has also found another solution to this problem, what it calls one-sided round-trip timing. So this simply measures the time taken to receive an ACK message and will work with any access point, regardless of how old it is. But the response time needs to be calibrated, and this can be done alongside the position determination process and added to the access point databases, but the accuracy isn't as good as using the FTM protocol, only 3 to 5 meters according to Google. So the next topic is augmenting Wi-Fi positioning with other technologies. So multi-sensor integrated navigation has been used in aircraft, ships, submarines, and cars for decades. However, the smartphone approach is typically switch on the GNSS receiver or Wi-Fi transceiver, get a position fix as soon as possible, and then switch it off again. Power management has been prioritized over position accuracy. But with more efficient GNSS and Wi-Fi chipsets constantly being developed, is it time to combine multiple positioning technologies and operate continuously? So first of all, let's look at multi-epoch navigation. So you start with an initial set of measurements. We can assume Wi-Fi in this case, and you compute a position. You then predict your solution forward to the next point in time, collect some new measurements, update that position, and then repeat. So we're using information from previous epochs in time to improve the position solution accuracy. So this reduces the impact of measurement noise, and when moving, it also reduces systematic errors. It also helps with the fact that Wi-Fi measurements are asynchronous. The mobile communicates with one access point at a time, and it enables a position solution to be maintained where there are insufficient measurements for a single epoch solution. So lots of advantages, and commonly used algorithms include the extended Kalman filter and the particle filter. So first thing I want to look at is pedestrian dead reckoning. So here we're using smartphone inertial sensors to detect steps, estimate the distance traveled, and this is accurate to between 1 and 10% depending on sophistication and calibration. And the PDR can be used to improve the performance of our prediction step in our multi-epoch positioning algorithm. Then let's take a look at indoor GNSS. This is traditionally considered an outdoor positioning technology, but we can receive some GNSS signals indoors, particularly if the receiver is near a window, but we need to carefully select which signals to use because many, probably most, will be non-line of sight. So with standalone GNSS, we may also have poor signal geometry. So signals coming from this direction, but no signals coming from that direction. But if neither Wi-Fi nor GNSS give a good position on their own, we can combine the two to give a better position solution. And improvements to GNSS are coming in the pipeline. A technique sometimes known as supercorrelation uses coherent integration times greater than a second on low-cost platforms that may be undergoing arbitrary motion. They compensate this motion using inertial sensors. They have clock compensation algorithms, and they will use the data-free GNSS signals or remove the data component. This technique massively increases the receiver sensitivity, so it enables GNSS to penetrate much further indoors than it does at the moment. And also, the carrier frequency tends to vary differently for reflected signals than it does from the direct signal. So if the receiver is matching the carrier frequency to the direct signal, this will attenuate most of the reflected signals. So it reduces multipath interference and weakens non-line of sight signals. And there's a link here to a video from focal point positioning that tells you a bit more about that technique. The next thing to consider is low Earth orbit satellite navigation. So GNSS currently uses mid-Earth orbit satellites, which means that the signals are weak, making them vulnerable to interference, and they don't penetrate buildings very well. Low Earth orbit satellites are 10 to 50 times closer to the Earth's surface. So you get much stronger signals, and there are also advantages in terms of the shorter orbital period for integer wavelength ambiguity resolution in precise positioning. But signal footprints are much smaller, so you need a lot more satellites to cover the Earth, increasing cost. Now, at the moment, there's a company called Zonar Space Systems that are developing a LEO satellite navigation system known as Pulsar. They plan to launch satellites that orbit 800 meters above the Earth with 100 times stronger signals than GNSS, and they're aiming for 10 times better accuracy than unaided GNSS. Their test satellite is being launched this year. So the business model of Zonar is that users will pay to access the service. So they'll be targeting at professional users and autonomous vehicles. And whether this is a viable model depends on whether they can raise enough subscriptions to pay for the system. However, it's very unlikely that we'll see this on smartphones simply because who's going to pay? Are the users going to pay? Are the network operators going to pay? Are Apple and Google going to pay? That's very unlikely. So I don't think we'll see this in smartphones. Let's have a look now at the next generation of beacon technologies. So Bluetooth 5.1 incorporates angle of arrival and departure measurement, which means we can do angular positioning. So if you have a transmitter on this bearing and another transmitter on this bearing, you can intersect the two lines, and that gives the user position. So with Bluetooth beacons, generation 5.1, sub-meter 3D positioning should be achievable with 2 or 3 beacons. And then a high accuracy distance measurement using phase-based techniques is currently being added to the Bluetooth standard. So combining this with the angular measurement should enable sub-meter 3D positioning with a single beacon. So, but you've still got the problem, as with any beacon system, the beacons have to be purchased, deployed, surveyed, and maintained. So these beacons are only going to be available where the building operator wants to provide a higher accuracy positioning service than that's available or already available from Wi-Fi. So I think it's going to be a limited deployment. Another interesting development is that ultra-wideband ranging is now being added to smartphones as part of the Fine Ranging or FireR consortium. So this enables centimeter accuracy under good reception conditions, and it's already supported by some iPhones with Android to follow. Now, an ultra-wideband only position will require 3 beacons for a 3D solution, but a single beacon can contribute to a multi-sensor navigation solution. But we have the standard problem of who's going to pay to purchase, deploy, survey, and maintain these beacons. Well, it's only going to happen if the building operator wants to provide high accuracy positioning for smartphone users. And if the building already has an existing proprietary ultra-wideband system, well, this isn't compatible with FireR. But FireR also supports ultra-wideband ranging between phones. So I think this phone-to-phone ranging is likely to be the main application of FireR ultra-wideband. So this then enables cooperative positioning for smartphones. So you have devices both measuring ranges to Wi-Fi access points at known position, and also measuring ranges between mobile devices at unknown position. And then the positions of multiple mobile devices using all of the different measurements can be solved together. And as well as cooperative positioning, this is also sometimes known as peer-to-peer and collaborative positioning. Also, we have new standards of mobile communications, 5G being deployed now and 6G under development. These now have positioning capabilities built in. So effectively, phone signals are moving from signals of opportunity to positioning infrastructure. And as the bandwidth of these signals gets higher and higher, the precision of ranging measurements improves. So we have two implementations of 5G and 6G. We have the medium capacity, medium range version, which is similar to existing mobile phone signals, where we have the problem of non-line of sight reception being a big problem, and only nearby base stations offering direct line of sight. So typically, we may only get one useful measurement. However, 5G and 6G also has a high capacity short range variant, which is similar to Wi-Fi. So this is going to have a similar positioning capability to Wi-Fi round trip timing, and the more base stations, the better. So it's essentially a standards issue. If 5G and 6G end up replacing IEEE 802.11 for Wi-Fi positioning, then for Wi-Fi in general, then we're going to be using it for short range indoor positioning. If it doesn't, then we'll stick with 802.11. Currently determining the correct floor of a building with Wi-Fi positioning can be difficult. So one solution to this is barometric height. So many smartphones now have a barometer which measures atmospheric pressure, and this varies with the height. So we can infer the height from the pressure measurement. But the problem is the pressure also varies with the weather. So we need constant calibration. So we either need a differential approach with a nearby reference station, or we need to calibrate using GNSS before entering the building, or we need to obtain the height from a map when entering the building. But once we've calibrated it, the accuracy of height from a barometer is about 1 meter, which is pretty good. We can use the camera on a smartphone, but there's the practicality issues that the user needs to point the camera. Repeating features is a problem, and image-based positioning is typically more computationally intensive than radio-based approaches. It's most important for augmented reality, which requires precise positioning and orientation, and that's already using the camera. So we're probably going to find image-based positioning finding home in the augmented reality engine rather than in the location engine. A joker in the pack is magnetic anomaly matching. Local magnetic fields are common in an indoor environment, so we can detect these and compare them with a database, providing we make measurements at multiple positions with a known distance between them, so that we can get a unique match. But as with any database-based technique, it's time-consuming to build it, and magnetic fields change when lights and equipment are switched on and off. So I think this is a last resort to be used if everything else fails. So I think future smartphone indoor navigation, well, we'll stick with Wi-Fi using signal strength and various round-trip timing protocols. I think we'll be using FiRa ultra-wideband phone-to-phone ranging. I think there'll be a GNSS element enhanced with supercorrelation, and we'll be using pedestrian dead reckoning with inertial sensors, both to support the supercorrelation and for positioning directly. And maybe we'll use short-range 5G and 6G if it starts to be used instead of Wi-Fi, and then maybe barometric height will be used if the other systems aren't giving us enough height accuracy. So to finish, the final thing I want to talk about is the divide between indoor and outdoor positioning. So currently, the dominant technology for indoor positioning is Wi-Fi, and for outdoor positioning, it's GNSS. Terminology: indoor positioning people like to talk about localization. Outdoor people like to talk about positioning and navigation. Indoor people talk about hybridization. Outdoor people talk about integration. Indoor positioning tends to derive from the computer science, robotics, and mobile communications communities. Outdoor positioning from the electrical engineering, avionics, and geospatial science communities. And then there's even different conferences. So IPIN is one of the main conferences for indoor positioning, and ION one of the main conferences for outdoor positioning. But let's look at the technology. So Wi-Fi, it works indoors, but it also works outdoors. So if there's streets with buildings, Wi-Fi positioning will work. GNSS usually works outdoors. It works partly indoors, and it's getting better with supercorrelation. Ultra-wideband peer-to-peer ranging and dead reckoning techniques will work equally well indoor and outdoor. So actually, there's not a great deal of difference between indoor and outdoor positioning technologies. And then what do we actually mean by an indoor and outdoor environment? Well, an office is clearly indoor, a street is clearly outdoor. But what about a railway station or a covered walkway or a colonnade? Are they indoor or are they outdoor? So we have these transition environments, and also the area around a normal doorway is also transitional. So in conclusion, there isn't really a major distinction between indoor and outdoor positioning. There are no indoor only or outdoor only positioning or navigation technologies. The boundary between indoors and outdoors is not always clear. There's just integrated navigation. Thank you for your time, everyone.
Okay, thank you very much, Dr. Groves, for that interesting presentation, for taking us through all the possibilities that are positioning indoor and outdoors we have. And now it's time for questions. Unfortunately, we have only 5 minutes for questions. So please, those of you who want to ask, you can tell me in the chat. Just if you tell I want to ask, I will let you talk. And if you have a presentation, I have a question, you can answer me. Okay, Valerie?
Hi, Paul. Can you hear me?
Yeah, all good.
Good. Nice to see you. I have a question. You being, I would say, like quite an expert in GNSS signal processing, what is the part that you would address in terms of being able to still use GNSS signals in this indoor or light indoor environments?
So I think it's primarily about improving the signal processing with extended correlation time, so signals can get further. So that's one important step. Selecting the right signals is important. So outdoor 3D mapping can help identify which signals are likely to be line of sight, which signals are likely to be non-line of sight. Outlier detection will work better if we just feed GNSS measurements into a multi-sensor positioning solution rather than trying to compute a GNSS only solution. So if we pull GNSS measurements, Wi-Fi round trip timing measurements, and any ultra wideband measurements into the same positioning algorithm, we can then look at all of the different signals and select the best signals of each type to try and get the most accurate positioning solution.
Thank you very much, Paul. So for those who were not here just before those 2 keynote speech, the IPIN community has been strongly working toward the launch of a new journal that is addressing seamless positioning between all kinds of environments in and out. So you see how important it is, and so I invite everybody to submit there and support this new journal.
Related to that, I think Wi-Fi round-trip timing measurements could be very useful outdoors. We may find that they're better than a lot of the GNSS signals.
Okay. Thank you, Valerie. Thank you, Dr. Groves. Okay, we have another question from Bingao. Please proceed.
You're on mute.
You're mute.
Hi, Paul. Thanks very much for the presentation. Very nice summary. So my name is Bing-Hao Li from University of New South Wales, Australia. I have a little question and one little comment. One is the Wi-Fi RTT you mentioned. For using Wi-Fi RTT for positioning, we need to allocate the slot for the round-trip measurement. So for 3 round-trip measurement, so you have to allocate 3 slots for it to measure. Is there any mechanism at this stage to control this slot?
I think it's for the software in the phone to determine. So that tends to be an operating system issue. My student Gibran knows a lot more about this than than I do, but certainly for the current round-trip timing protocol, I think hogging the duty cycle is actually a major problem. So I think we may see round-trip timing becoming more established using the new Wi-Fi 6 protocol rather than the existing fine time measurement protocol.
Thanks. For another little comment, it's actually for outdoor positioning and indoor positioning. So there is a big community, not big, small community, joined both. It's surveyors. The surveying community joined both.
So yeah, I mean, I think there are quite a few people that join both, but it is still 2 separate communities with different terminology, and there's also differences in terminology between the surveying community and the navigation community. So surveyors talk about observations and navigators talk about measurement, even though it's the same thing.
Thanks, Paul.
Okay, thank you very much, Bing-Lao. Thank you very much, Dr. Groves. I'm very sorry, but we are with a very tiny schedule, so we have to take the end here. Unfortunately, we cannot say that we can still talk in the coffee break. But I invite you to join us to the next sessions that will be for sure so interesting that this keynote has been. And thank you very much for you all for attending. Thank you very much to IPIN organizers for letting us the opportunity to attend these interesting keynotes and this wonderful Congress. So thank you very much.
Oh, thank you. It's wonderful.
Thank you, Tony. Thank you, Professor Paul.